Welcome to EDU World Space.
Here we're going to examine the behavior of a small charge caught in between two equal charges but constrained to move along the line joining them. And we'll see what happens when that small charge is displaced by a distance s. So there's some things that we're going to need. First of all, we are going to set up the force, net force, on that little charge by finding the total electric field acting on it. So those two charges, as the charge gets displaced in the center, will have different magnitudes, with E1 being a little bit weaker and E2 being a little bit stronger. And so we can use the magnitudes of those to calculate the x component of the force on that little charge. And that x component will govern the mass times the acceleration of the central charge, which has mass m. Okay, so that is our goal, is to find that net force. Of course, we will need Coulomb's law. So the magnitude of the electric field from a point charge is K, the electrical constant, times the Q over R squared. I'm also going to write down Hooke's law. We won't work with the differential equation we get, but just by analogy, we'll look at Hooke's law, which says if you have a force that is proportional to the displacement, you basically wind up with simple harmonic motion with angular frequency equal to the spring constant, Ks over m. And that's also related to the period of the oscillation. Hooke's law is the force law. The simple harmonic motion comes about from solving Newton's second law for that type of force. Okay, so we're ready to put in, once we figure the force out, and that it indeed undergoes simple harmonic motion, we'll look at a simple numeric example. Okay, so let's put in the two electric fields. The electric field number one is a little bit weaker. Yeah, let's put all the constants out front. Okay, so the separation between the little q and the big Q to the left gets a little bit bigger, and it gets a little bit smaller to the right, the way I've drawn it. Okay, now to simplify this, what we're going to be doing is using the binomial approximation, which is a very handy tool to linearize things. What this says is if you have the binomial 1 plus delta, and you raise it to the nth power, and that could be either plus or minus delta, that is approximately 1 plus n delta. And it works for negative exponents n or positive exponents n. But you must have delta much less than 1. Okay, so it's an approximation, and in our expressions, we can take something like 1 plus d to the s plus s squared in the denominator and approximate it in our nice binomial form. Okay, because we have with once we take the d squared out, we see that we have 1 plus delta raised to the minus second power. So that is an approximation for the first term, and we can do a very similar thing for our second term. And then if we add those two terms together, actually not add them, but subtract them, we see that we are left with minus 4s over d cubed. Okay, so the constant term disappears, and we are left with twice minus 2s over d cubed. So we can now, after that approximation, okay, so reminder, that is an approximate thing using the binomial approximation. We can now write our x component of force as q, little q, big Q, electrical coefficient, and then minus 4s over d cubed. And yeah, I can rearrange that so it looks more Hooke's law like, with a lot of constant numbers out in front. I'll put those all in parentheses for little q, big Q, electrical constant divided by d cubed times the displacement s. So yes, a force law that we have found from those two electric fields looks like Hooke's law. And the quantity in parentheses, we are going to call it our spring stiffness or spring constant. And now we know that the acceleration, the second derivative of s, is proportional to s with a negative sign. And so the charge will oscillate, little q will oscillate. And after using that in our period relationship, 2 pi over the period is spring constant over m square root. We can rearrange that, and we come up with a formula for the period. It is 2 pi m over the spring constant, where the spring constant, I probably don't want to plug all that in. It'll look a little bit messy, but we do know what that constant is. And here's where things get a little bit awkward. There's two k's. One is the electrical fundamental constant of electricity. We'll get to that. The other is a particular spring constant. So yeah, let's do an evaluation. Let's try to find the oscillating period if we somehow have a sodium ion in a crystal stuck between two other fixed sodium ions. Okay, so we're going to make all the charges equal to each other and equal to the fundamental electrical E. We are going to need, well, we have the electrical K is 8.99 times 10 to the ninth in newtons times meter squared over coulomb squared. And we are going to need the D, the spacing, which we are just going to approximate as 3 times 10 to the minus 10 meters. That is a good size of an atom. May not be perfect, but we'll go with it. And then the mass of a sodium atom is 22 atomic mass units. And I am using 1.67 times 10 to the minus 27 kilograms for the atomic mass unit. Okay, and I'm not going to show all the calculations, but that shows all the numbers being used. I will show the intermediate spring constant is for, I'm winding up with 34.1 newtons per meter. Newtons per meter when I use all the values in the equation there. Check that out. And so my period then is quickly found from the mass. Divided by the K, spring constant. And if I have used SI units, the period should wind up to be in seconds. And I will go ahead and convert it into picoseconds. So I'm getting a fraction of a picosecond. So that gives you an idea of how rapidly an atom will vibrate stuck in a crystal. Okay.